Okay, welcome to part 3 of correlation, and this time we're going to be talking about the chi-square test for association. It's also sometimes referred to as the chi-square test for independence. So just as you use different software, just know that we can use either name. It's used to determine if a relationship exists between two categorical variables, and it's important to think of this for nominal variables only, so nominal being non-ordinal variables. Can you use the chi-square test for ordinal variables like Likert scale items? And the answer is yes, but you lose the ordinality nature of the variables. The way the chi-square test works is by only assuming that nominal characteristic of the data. An example could be looking at geographic locale, so living in a non-rural or rural area, and political affiliation of Democrat or Republican. And I'm trying to do a simple example here that is what would be called a 2x2 example because we have only two options for locale and two options for political affiliation. The test generates a contingency table, which can also be called a cross-tabulation, and it displays the cross-grouping of the categorical variables. And we'll see that in more detail in a minute. The chi-square test checks the null hypothesis that there is no association between the two categorical variables. And how does it do this? It compares the observed frequencies of the data in the contingency table or cross-tabulation with that would be expected if there was no association between the variables. All right, so how do we get there? What is expected versus observed? So on the left, we see an equal distribution for 100 randomly selected people. We see 25 in each group, so 25 non-rural Democrats, 25 non-rural Republicans, 25 rural Democrats, and 25 rural Republicans. Again, that uniform or equal distribution. But then when we actually went and observed political affiliation by locale, we found different numbers. We found 50 non-rural Democrats, 7 non-rural Republicans, 8 rural Democrats, and 25 rural Republicans. All right, so how do we get to our expected numbers? So the model, or the expected value, is the row total times the column total that we observed divided by 100. All right, so for non-rural Democrats, that would be 57, the row total, times 58, the column total, divided by 100, which would give us the 33.06 in green. So 50 is what we observed, 33.06 is what we would expect. Similarly, for a rural Democrat, we would do 33, the row total, times 58, the column total, divided by 100, giving us 19.14 expected rural Democrats, when in fact we observed only 8. And we could do the same thing for the non-rural Republicans and the same thing for the rural Republicans. And then the chi-square statistic is calculated as the sum of the observed minus expected squared divided by the expected. All right, but again, that is what the software does for you. All right, so what are our assumptions here? The assumptions are that both variables are categorical, and again, we mean nominal. We have independence of observations. So what do I mean there? That means there's no relationship between the observations in the groups of the categorical variables or between the groups themselves. All right, so an example here, what this is really saying is that no one can be in the rural Democrat group and the non-rural Republican group. All right, so an individual or case only appears in a single grouping, in a single cross-tabulation. And lastly, which is really important, is that all cells should have expected counts greater than 5. All right, so let's go to our JASP example. All right, so we wish to explore the correlation between geographic aspirations at age 30, and here we have 1 is non-rural, 2 is rural, and 3 is don't know, and gender, where 0 is male and 1 is female in high school students. Notice both variables represent nominal variables. All right, so let's escape out of this and let's pull up JASP. All right, and what we want to do in JASP to run the chi-square test for association is go into frequencies and go under classical contingency tables. And we are going to put rural aspirations at age 30 in rows, and we're going to put female in columns. It could go either way. It doesn't matter which one we do here. And then under statistics, we're going to check chi-square continuity correction also, as well as likelihood ratio. And then under nominal, we're going to check contingency coefficient and phi and Kramer's V. In cells, we're going to check expected. And for percentages, we want row and column. Okay? And here we see our contingency table with our observed, which is the count, and our expected, which is the expected count. We get results for chi-square tests, which I'm going to talk about in a minute. And then we get this nominal table with that contingency coefficient as well as the Kramer's V. So let's go through what exactly these results are telling us. Okay, so first let's think about the assumptions. Both variables are nominal. We have independence of observations, so a female could not have said rural and non-rural. There was only one response recorded. And if we look at our expected counts in the table, we see that everything is greater than 5. So our 3 assumptions are met. All right, and now let's just kind of descriptively look at our table a little bit. And here, remember 1 for rural aspirations is, or for aspirations is wanting to live in a rural environment. And let's look at wanting to live in a rural community across gender. And we see here that more males are saying that they expect to live in a rural community than what is actually expected. And we see the opposite relationship for females, where we observe 114 females wanting to stay in a rural community, whereas the expected number is 134. All right, so let's interpret the chi-square tests. All right, first we see a chi-square test, which suggests there is a significant association between gender and geographic aspirations. And we see the chi-square value of 12.865 with 2 degrees of freedom and a p-value of 0.002. All right, so again, that significant p-value is saying there is an association. The chi-square continuity correction can be used to prevent the overestimation of statistical significance for small data sets. It's mainly used when at least one cell of the table has an expected count smaller than 5, but you want to be really careful using the chi-square continuity correction. It sometimes can overcorrect, causing a type 2 error. So again, remember that type 2 error is that you fail to reject the null when you really should. All right, but when you are working with a small data set, you may want to use the likelihood ratio. It's an alternative to the chi-square test. And for large sample, it is identical or nearly identical to the chi-square. But it is recommended for small sample sizes, and particularly when that sample size is smaller than 30. But in our example here, with over 1,000 students, we see that it is practically identical to the chi-square. All right, so One thing we want to think about is the strength of the association with the chi-square. And we have contingency coefficient results and Cramer's V results. And then we also see that there is the phi coefficient, which I had you check, but that we cannot actually get results for here. First and foremost, phi is only available for 2x2 contingency tables. So again, where each variable has only 2 options to it. And in this working example, we have 3 options for geographic locale. So that does not give us results. All right, the most popular between the contingency coefficient and Cramer's V is definitely Cramer's V, so I recommend interpreting that for the strength of the association or effect size. And here's an effect size table for you guys based on the degrees of freedom of the test. So remember, we had 2 degrees of freedom in the chi-square test. All right, and for 2 degrees of freedom, Cramer's V gives us a small, moderate, and large effect size. Our Cramer's V for this problem is 0.105, and we see that 0.105 falls between small and moderate, so we see we have an effect size of small to moderate. All right, what about reporting results for chi-square tests for association? All right, we would start by saying a chi-square test for association was conducted between gender and geographic aspirations at age 30 for 1,176 high school students. All expected cell frequencies were greater than 5. There was a statistically significant association between gender and I don't know where that came from, but let's just say between gender and geographic aspirations. And when you report this, you're reporting the chi-square with the degrees of freedom in parentheses, so we have 2. And then you report the chi-square value of 12.865, and then you report the significant p-value of 0.002. What if there had not been statistical, or here, our effect size, we could go on to say there was a small to moderate association between gender and geographic aspirations at age 30, and there we would report Cramer's V as a capital V equal to 0.105.